Welcome to part 3 on the Central Limit Theorem. Let's get started. Let's start by recapping the problem we're trying to solve here. So the problem is the true mean height of Sasquatches really 8 feet as claimed when the last 10 random sightings give an average of 7.54 feet? So we've learned so far that this difference in means alone is not enough evidence to decide, because the difference between the sample and the assumed mean could just be due to the variance inherent in the Sasquatch population's heights. So, because of sampling error, the logic of an answer to this problem becomes a little more complex. So let's finally list out the steps then of the inferential way we'll need to answer this problem. That is, how we'll go about accepting or rejecting Woodland Pete's claim that the true mean height of Sasquatches is 8 feet. So first, we'll need to calculate the likely range of means that can be expected for a random sample to arise out of the variance in the population alone. Because if the 7.54 feet we observed is outside what was likely, then we would have logical evidence that says the true population mean height is not likely 8 feet after all. When we model a population with certain assumptions, but then the laws of random sampling tell us that the population as assumed would be extremely unlikely to produce the real-world sample mean we observed, then we have reason to doubt the assumptions are true. Of course, this also assumes that our real-world sampling technique was good, or random. These laws of random sampling that I'm talking about are what the CLT is about, and will be the subject of this video. They help us complete step 1 and infer in advance the range of means we'd likely see in a sample taken randomly from a population with an assumed mean and an assumed standard deviation. As we start to explore the CLT, let's first establish a definition of what we mean when we say an outcome is, quote, unlikely. So one very common probabilistic definition, and the one we'll adopt, is that something is unlikely if it has less than a 5% or a 1 in 20 chance of occurring. So what does this look like on the normal model? Recall the empirical rule that says that 95% of the population will fall within 2 standard deviations of the mean. This, of course, leaves 5% of the population falling outside of 2 standard deviations. So this leaves 2.5% of normal data in this right tail. Everything here has a z-score of greater than +2, and it leaves 2.5% of normal data in this left tail having a z-score of less than -2. So that's a total of 5% outside of this range of ±2 standard deviations from the center. When we observe one individual datum at random then from a normal distribution, it has only a combined 5% chance of being from one of these tails, that is, of having an absolute z-score greater than 2. And by our definition then, any absolute z-score greater than 2 is unlikely. Let's take the example of flipping 100 coins again. We know that when data has variance, a sample of it might not give the exact true mean. Because, for example, flipping 100 coins, we might get 52 tails, but this doesn't prove bias in the coin because we know intuitively this result isn't that unlikely, given the random nature, the variance in a fair coin. But if we start to get more tails, 60, 75, at what number precisely can we say that something other than randomness alone, like a true weight imbalance on the coin, a real bias in the coin, appears to be at work? The CLT is what allows us to answer questions like these. As the law of random sampling, as we could call it, the CLT tells us in advance the means that we're likely to see in random samples taken from a population with a given mean and variance. It says that as n increases, as our samples get larger, this range of possible sample means, first, becomes normally distributed even if the population's original distribution is not normal, and then second, that the sample mean will converge on the true mean. This is perhaps the most important idea in all of statistics, The central limit theorem is what allows us to reach logical conclusions with only partial knowledge of the whole, with only a mere sample of a population. To see how to demonstrate the CLT and see these two attributes at work, let's perform a quick experiment. What we're really interested in here is the precise variance, the error in sample means that's possible since samples of the same size from the same population can deliver a variety of different means. So, if we're interested in knowing how samples from the same fixed population can vary, why not repeat the same sample of the same n many times, chart all of the sample means we get, and see what we get for variance between all of them? Because we know n increases accuracy. So we just need to repeat the same sample enough times, and the size of this sample of samples will eventually be large enough that we can be sure it's giving pretty accurate results of how sample means truly vary for a fixed n. We'll be able to spot the mathematical pattern if there is one. Let's start with the smallest sample possible, sampling one coin flip at a time, that is n equals 1. And let's take 100 samples of these. And just trust me when I say 100 will be enough samples of samples to see this central limit theorem at work. Let's also go ahead and assign heads a value of 0 and tails a value of 1 so we can convert our flips into binary data we can do math with. Note that when we run a simulation of 100 samples of n equals 1, because each sample has only one member, each sample's mean will be its own value, that is 0 or 1. Now, because a sample of n equals 1 is equivalent to selecting a random individual from the population, you might be thinking, isn't this the same as one sample of 100 individuals? That is 100 flips? And you're right, but we're currently interested in seeing how means vary between samples. So that's why we've set things up like this. So running the simulation, how many means of 0 and how many means of 1 will we get out of 100 samples? And what will be the mean of these 100 means? And how will these 100 zeros or ones vary around this mean of means? This is all better shown than explained, so here we go. Out of 100 samples, taking the mean of each sample of 1 every time, we got 49 means of 0 and 51 means of 1. Overall, this averaged into 0.51. We're calling this our mean of all these means. The variance of all these means is this number, 0.2524. Recall how variance is calculated for a sample. This number is the n-1 average that all these means are away from the very center. It's their average squared difference from the very center. And this makes sense. 0 and 1 are both about 0.5 away from this, and squaring that number gives about 0.25. So why did we take the means of samples of only n equals 1 first? Samples of 1, of course, are equivalent to sampling individuals, and taking the mean of one individual doesn't do anything. So what we've actually obtained here is the data's own variance. The variance, we can assume, is inherent in the population itself. But I wanted our process to be consistent. We'll bump up n to 10 next. But this exercise gave us a baseline so we can see what happens to the variance of sample means as we start to increase sample size. This way, we can expose and measure the central limit theorem's effects. Importantly, too, note how at this point, the data, what we assume is representative of the population, has a uniform distribution. That is, every outcome out of 2 has a nearly equal chance of occurring. It's not a normally distributed population that we're working with. Now, let's bump up the sample size to n equals 10 and simulate 100 samples of 10 flips each. How will the sample means vary now? Of course, with n greater than 1, the mean of each sample will no longer equal 1 or 0. For example, you can see the first sample of 10 flips gave 4 tails for a mean proportion of 0.4. After taking 100 of these sample means of 10 flips each, the mean of all means was 0.486, which is very near a fair coins, that is the assumed population's, expected central tendency of 0.5. In the rightmost column of this truncated table, you can see each sample mean's squared difference from the overall mean. Then the n-1 average of all of these gives a sample variance of 0.0247. Recall that the variance in the coin itself was 0.25, so this new variance is 1/10 of the original variance in the population. The variance, also known as error when we're referring to a distribution of sample means, has decreased because when you average 10 flips instead of just one, you mostly get 3s, 4s, 5s, 6s, or 7s. In fact, 91 out of these 100 10-flip samples had a mean between 0.3 and 0.7. 61 of the samples had a mean between 0.4 and 0.6. An error of 0.025 converts into a standard deviation of about 0.16. Importantly, note that this standard deviation of a distribution of sample means has a special name in this context. To keep it distinct from the standard deviation of data, to designate it as the standard deviation of the means of sampled data, it's called standard error. That's why there's SE in parentheses here. This plot of our 100 samples of 10 flips each shows us that when we take an average measure, now of n equals 10 individuals instead of a single n equals 1 individual measure, the possible sample means begin to form a normal distribution around the true mean of 0.5. This is the CLT at work. As n increases, it says that random sampling will produce more sample means close to the central tendency and less at more extreme means. And remember how I pointed out that the coins distribution was not normal, but uniform? Even though the population's distribution is not normal, now that we're averaging 10 individuals together in each sample, we're already getting sample means roughly falling into a normal distribution, with 10-fold less variance. But we're interested in learning a general rule of how sample means vary for any sample size, that is, any n. So what would happen if we were to increase our sample size to 100 flips per sample? Here are the results of that simulation. Remember, out of our 100 samples of n equals 10 flips per sample, 61 showed a proportion of tails between 0.4 and 0.6. Now, out of 100 samples of n equals 100 flips each, 98 of them have a proportion of tails between 0.4 and 0.6. You can see this in the variance, or error, that is the average squared difference of each 100 flip sample from the central tendency of very nearly 0.5. It's now only 0.0026, 100 times smaller than the original 0.25 variance of one individual coin flip. With sample size up tenfold from n equals 10, the sample means are varying another factor of 10 less from the central tendency. You can see this visually in our plot in how tightly the sample means are converging in a normal distribution around the true central tendency. Let's summarize our coin flip experiment. For all sample sizes, all n, the true central tendency has shown through. The mean of means, or the overall mean, has always been very near 0.5. But the variance of the sample means has been shrinking as n increases. So our experiment has been showing the CLT at work, that as promised, as n increases, the range of samples means, 1, becomes normally distributed, even if the population isn't normally distributed. And 2, they converge around the population's true mean, i.e. the error of the sample mean decreases. But what's the mathematical pattern? Looking at our summary table, the general rule is, as n increases, the variance of the sample mean decreases, or divides, by a factor of n. We kept increasing n by a factor of 10, so the variance of the sample means kept decreasing by a factor of 10. The numbers in our experiment summary table still have a little noise in them because they are still sample data. But distilling from what we know is true about a fair coin, the central tendency, the overall mean, should always be 0.5, and the original variance, thus, 0.25 even, and so on down the line. Of course, according to the CLT, if we had sampled more than 100 trials each time, our sample numbers would be even closer to the expected numbers. So, rounding these values from their sample numbers to their ideal expected numbers, we can derive several formulas. The expected population variance, denoted by sigma squared, is the variance found between individuals in the population, in this case for single coin flips. So for a fair coin with an expected center of 0.5, the individual variance is 0.25. And because standard deviation is just the square root of this, the standard deviation of the population is expected to be 0.5. Now, where n is greater than 1, the expected variance of the distribution of sample means is sigma squared divided by n, the original population variance divided by n. Because standard deviation is always the square root of variance, the standard error, that is the standard deviation of the distribution of sample means, is the square root of error. So, for example, 0.025, the square root of that gives you 0.16. This formula simplifies into sigma divided by the square root of n. So 0.5, the original standard deviation, divided by the square root of 10 gives you 0.16. What does 0.16 mean for samples of 10 flips? What does 0.05 mean for samples of 100? What is standard error? This is important. Taking samples of 100 flips each, the expected mean, or proportion of tails, of those samples will fall into a normal distribution. And this normal distribution will have a standard deviation, called standard error, of 0.05. Remember the empirical rule then, which says that 68% of anything normally distributed will fall within one standard deviation of the mean. So for a normal distribution of sample means of 100 flips, 68% of the time, about 2/3 of the time, the sample mean, the proportion of tails, will be between 0.5 plus or minus 1 times the standard error, 0.05. In summary, that means 68% of sample means of samples of 100 flips should be between 45 and 55 tails. A mean of 0.45 to 0.55 is what we'd expect from sample means of 100 flips. Don't worry if the idea of standard error is still a little fuzzy. We'll keep coming back to it as we go along. One thing else to note, we've also happened to demonstrate that for binary data like coin flips, you actually don't need to measure standard deviation and variance separately. It's enough just to know the mean. Why? Well, the mean of binary data, often called p instead of x bar, already tells you its variance with p times 1 minus p, because binary data can only vary between 0 and 1. So notice that there's no sigma or sigma squared in this formula for standard error. If you want a deeper understanding of why this is the case, you can hang on at the end of this video and I'll give a quick demo of the math. These formulas we've demonstrated are very useful. With them, we can predict how the means of samples from a given population will distribute given just that population's own center, variance, and our sample size n. And we know that even with non-normal population data, the means of samples from that data will be normal, and with a variance equal to the population's variance divided by a factor of n. So the upshot of this is we can use the normal model, z-scores, on the standard normal distribution to find the likelihood of observing any range of sample means given just the population's parameters. In summary, the normal sample means curve, the SMC as we'll call it, can be constructed from the population parameters alone. The SMC has a mean center mu, the population's own expected center, and a standard deviation called standard error equal to sigma over the square root of n. That is, the population's inherent standard deviation divided by our sample size. Now that we know we can use the normal model to map the SMC, we know that we can also use z-scores to find the likelihood of any particular sample mean value. So the only question is, how should we define what an unlikely sample mean is? Well, if we stick with our current definition that unlikely means a less than 5% chance of occurring, and we know that the SMC is a normal distribution, then we can also say the mean of a sample is unlikely if it's more extreme than plus or minus 2 standard errors away from the expected sample mean. That is, it has an absolute z-score of greater than 2 on the SMC. An equivalent way to think about this definition of unlikely, then, is as anything outside of a 95% likely range, because every probability has its complement, which is 1 minus it. Here, a 100% chance of everything minus 5% unlikely, or 2.5% unlikely to the right, 2.5% unlikely to the left, leaves 95% likely. On the normal SMC, then, the 95% likely range is everything within plus or minus 2 standard errors. And unlikely means anything outside of this range. That is, if a sample mean's z-score is greater than plus or minus 2, that means it's from one of the 2.5% tails on the sample mean's normal curve, and it gets designated unlikely. The 95% likely ranges are easily calculated then for our different sample sizes. We just use this simple formula. We take the population's expected center mu plus or minus 2 times standard error. 2 coming from the empirical rule to give us the 95% likely range for any normal distribution, and standard error being particular to the standard means curve, the SMC, whose standard deviation is SE. The 95% likely ranges are easily calculated then for our different sample sizes. And this last entry actually answers a question we've been asking, namely, out of 100 flips, what's a suspicious or unlikely number of tails to get where you might start to think that coin is biased? Well, we did 0.5 plus or minus 2 times the standard error of 0.05 to get a 95% likely range of 0.4 to 0.6, meaning 95% of the time in samples of 100 flips, you'd get a proportion of tails between 0.4 and 0.6. You get 40 to 60 tails 95% of the time. So if you got something like 39 or less, or 61 or more, you have reason, under this definition of unlikely, to think that this coin is giving an unusual result. It's giving a result from one of the 2.5% tails. So, have we finally put this question to rest definitively? That if you have a coin which gave 39 tails out of 100 flips, we've proved that it's biased once and for all? Well, you can see we're dealing with probabilities here. A result of 39 tails or less out of 100 flips still has a 2.5% chance of occurring in a truly mathematically fair coin. And this, unfortunately, is as far as statistics will take us. It's up to us, that is, to define the probability that's finally small enough that we can rule something, quote, definitively proven. But let's try a bonus question. What's the 95% likely range of the sample mean for samples of 1,000 flips? Pause the video quick and try it. So to solve that, you take mu again, the expected center, plus and minus 2 times a standard error. For 1,000 flips, it's the original standard deviation, 0.5, divided by the square root of 1,000, which gives a 95% likely range of 0.468 to 0.532, meaning out of 1,000 flips, 95% of the time you'd expect to see between 468 and 532 tails. Finally, one last but very important note about this likely range. Careful not to confuse it with a confidence interval if you've already heard of those. The likely range is calculating the range of values we would expect to see for a sample mean 95% of the time in repeated samples of the same size in samples from the assumed population. That is, assuming that the center mu is the true center of the data. That's why we've adopted the population's own mu in constructing the 95% likely range. On the other hand, a confidence interval is very similar but works from a different assumption. It does not assume that the population center mu is the true center. So instead, it takes the sample's mean, x bar, not mu, as the best estimate of the true mean, and then uses that as the center of an interval estimating the likely true mean. Don't worry if that's still a little fuzzy. We'll come back to confidence intervals in the next video. So it's that time again to go over the key points. Remember our question from part 1, which was, given a population with variance, can we infer how the means of samples from that population will vary? In this video, our coin experiment showed that yes, thanks to the Central Limit Theorem, we can infer that. The variance of sample means will be the population's variance reduced by a factor of n. And the sample means distribution, or the sample means curve, will be normal. So we can use z-scores to find the probabilities of any given sample mean. And now, just for the love of more visuals, here's the coin experiment data again, but with everything on the same scale. Note how the n equals 1 data, representative of the population distribution, is not normal, it's uniform. But the distribution of means in samples where n is greater than 1, they are normal, and they're narrowing as n increases. The expected means spike higher and higher at the central tendency. We can use the statmagic app to see the CLT at work. In the normal distribution calculator, this time choose X bar mode because we're going to be looking at distributions of sample means. From our coin example, mu is 0.5, the standard deviation was 0.5, and let's start with an n of 10. Just ignore the z versus t toggle for now. So first, let's calculate the probability that a sample of 10 flips gives a proportion of tails between 0.4 and 0.6. Hit calc, and there you go, z-score is included. But why now are there two curves? Well, the flat one in the background represents the population if it were normal, but remember it doesn't have to be. The taller, more narrow one in front is the sample means curve, the SMC. Now the relative heights of these curves shows the relative frequency and hence also probability of observing any given value. So you can see that the probability of observing a value central to this population is higher when you take a sample of 10 flips and average them all, as opposed to taking a single flip. Now let's say we bump up the n to 100. Hit calc again, and what's happened? You can see that the SMC narrows towards the center even more, which says the sample mean of an even bigger sample will be even more likely to give you a value near the population's true mean. The probability of a sample mean falling between 0.4 and 0.6 is pretty large now, over 95%. Bump n up to 1,000, and I bet you can guess what will happen. The probability of seeing a sample between these two bounds is almost certain. In fact, it's rounding to an even 1. And this is the CLT visually. Your odds that a sample's mean will reflect the population's true mean increases with sample size. To get back to the main question of this series then, how does what we've learned about the Central Limit Theorem apply when it comes to finding the true mean height of Sasquatches? Well, it would help us to calculate how likely a sample mean of 7.54 feet was, assuming the mean population height really was 8 feet. So to finally bring it all together and answer this one, check out the next video where we'll walk through hypothesis testing and practice some of the fuller logic of this type of inferential statistics. And finally, as promised, here's the math showing how the variance of binary data, the variance of proportional data, can be simplified down to p times 1 minus p. First, here's the general form of variance. You remember it's the average squared difference between every data point and its mean. But binary data is not continuous. It only comes as a 0 or a 1. So we can rewrite this average squared difference formula as so, where you have the number of zeros there are, and then the squared difference between 0 and the center P, plus the number of 1s there are, times the square difference of 1 and the center P, all over the total number of observations, the number of zeros plus the number of 1. Now secondly, we know that P is simply the number of 1s, or successes there are, over the total n, and then 1 minus P is just the number of zeros over the total n. So throwing these identities for P and 1 minus P back into the equation, we get this, and consolidating it, we get this, consolidating some more, and then recognizing what's there, we have these same identities again, which it's simplified down to P times 1 minus P gives you the variance for binary data. So if we go back and look where we discussed the formula for standard error being the population standard deviation over the square root of n, well, if binary data's variance is P times 1 minus P, its standard deviation is the square root of that, and so the standard error of binary data is the root of P1 minus P over n.